Now that we've got access to the outside-in approach to the chain rule, what I'd like to do is take a look at a couple of examples. First one I'd like to do is f of x is equal to the square root of the sine of 3x plus 1. Now when it comes to square roots, there is something that we should do right away. And the thing that we're going to do right away is turn this into a 1/2 power. Now when it comes to this multiple applications of the chain rule, I want you to think to yourself, what is the outermost function in this case? Now we do have an inner function of the sine of 3x plus 1, but our outermost function in this case would be a 1/2 power. It is because of this that according to the chain rule, the first thing we're going to do is apply the power rule. So for f prime of x, the power rule states we multiply by the current power and reduce the power by 1. 1/2 minus 1 will be equal to negative 1/2. Now the chain rule says that we are going to multiply by the derivative of whatever's inside. Now, to hopefully be clear, whatever goes in here is going to go over here as well. The thing that we had on the inside was the sine of 3x plus 1. So that is what I'm going to be differentiating out here. However, when we take a look at this, we do have another composition of functions. Our outermost function in this case is the sine of something, which is why we're going to think to ourselves, what is the derivative of the sine function? So this part's going to stay the same. And for our derivative, we are now going to take the derivative of the sine function, which is the cosine function. And because the inside was not simply x, once again, the chain rule says whatever was inside here is going to go inside here as well as inside here. That'll be 3x plus 1 and 3x plus 1. Evaluating this derivative, because it's linear, will simply be 3. So it'll be 1/2 times the sine of 3x plus 1 raised to the negative 1/2 power times the cosine of 3x plus 1 times 3. Now at this stage of the game, our calculus is done, so anything else that we do to it after that would simply be an algebraic or trigonometric operation to pretty it up. We will have a fraction here due to the fact that there's already a denominator, and we do have a negative 1/2 power. So we'll call that the square root of the sine of 3x plus 1 in the denominator. Your numerator can get the 3 as well as the cosine of 3x plus 1. That'll be our final answer for f prime of x. Moving on to our next example. G of x is equal to the cosecant of the cube root of 4x squared plus 2x. Now once again, similar to what we did on the previous problem, I'm going to refer to this as the cosecant of 4x squared plus 2x raised to the 1/3 power. Just something that we would typically do anytime we're dealing with any sort of radical. Now in this case, we're going to think to ourselves, what is the outermost function here? The outermost function in this case is the cosecant function. So the first layer that we peel back for the chain rule is going to be that cosecant function. The derivative of the cosecant function is the negative cosecant function times the cotangent function. Now because the inside of that cosecant function was not simply x, that's where we're going to see the chain rule pop up once more. So the thing inside the parentheses was 4x squared plus 2x raised to the 1/3 power, and that'll go in all of these blanks. Now our outermost function for our next derivative is going to be the 1/3 power. And for that 1/3 power, we can apply the power rule. So the first part's going to stay the same, negative cosecant of 4x squared plus 2x to the 1/3 power times the cotangent of 4x squared plus 2x raised to the 1/3 power. Now we apply the power rule. Our power is currently 1/3, so we will multiply by the current power and reduce the power by 1. 1/3 minus 1, get a common denominator, you'll have negative 2/3. The chain rule says whatever was on the inside, we're going to multiply by that derivative next. Like so. Now this derivative will not require the use of the chain rule, this one will just require the use of the power rule. So we'll wind up with the negative cosecant of 4x squared plus 2x to the 1/3 power times the cotangent of 4x squared plus 2x raised to the 1/3 power times 1/3 4x squared plus 2x to the negative 2/3 power, and finally we'll be multiplying that by the derivative of 4x squared plus 2x, also known as 8x plus 2. Now if you're interested in doing something similar to what we did for the previous problem, that would probably help clean this up a little bit. We'll maintain that negative in front of the fraction. The cosecant and the cotangent can both go up top. So cosecant of 4x squared plus 2x to the 1/3 power times the cotangent of 4x squared plus 2x to the 1/3 power. The 1/3 can be a 3 in the denominator. The negative 2/3 power can go into the denominator as a 2/3 power. We'll call that 4x squared plus 2x to the 2/3 power. If you wanted to, you could also say it's the cube root of this quantity squared. And finally, we'll toss the 8x plus 2 into the numerator as well. So, final answer for that one is this lovely thing. It's problems like this that make me really excited for Calc 2 when we start doing this stuff backwards. We say, here's the derivative of a function, figure out what the original function was. Whew, can't wait. Super exciting. I do have one more example I'd like for us to try out. This one's going to bring in several rules for derivatives. We have the secant of 2x divided by 1 plus the tangent of 2x, and the whole thing is raised to the 4th power. We're going to differentiate this. Our outermost function, in this case, is going to be a 4th power. As such, we can apply the power rule. So h prime of x is going to be equal to 4 times this monstrosity raised to the 3rd power. Because the thing inside there is not simply x, we're going to tag on the derivative of whatever that thing is. That thing in this case happens to be the secant of 2x over 1 plus the tangent of 2x. That'll go out here as well. Secant of 2x divided by 1 plus the tangent of 2x. This is not a composition of functions, rather, this is a quotient of functions. Because it's a quotient of functions, that's why I'm going to be making use of the quotient rule. So the first part is going to stay the same for the rest of the problem. So 4 times the secant of 2x divided by 1 plus the tangent of 2x raised to the 3rd power times. This is where we'll be making use of the quotient rule. Quotient rule states that this will be low, d high, so derivative of the secant of 2x, less high, secant of 2x, d low, that'll be the derivative of the denominator, over the square of what's below. Now, both of the terms that we're still to differentiate in the numerator are both going to require the use of the chain rule because it's the secant of something that's not just x and the tangent of something that's not just x. So again, first part's going to remain the same. However, because this derivative and video already seem long enough, we are going to make use of the shortcut from the previous video. The shortcut was anytime you're differentiating something where it's just one use of the chain rule and the thing on the inside is linear, then we have a special shortcut for that. So this will be the derivative of the secant function, which will be the secant times the tangent. Input stays the same. And then the chain rule says we multiply by the slope of whatever this was, or the derivative of 2x. That would be 2 in this case. Minus the secant of 2x times this derivative. Derivative of 1 will simply be 0. Derivative of the tangent of 2x will be the secant squared of 2x. Chain rule says multiply by 2 due to the fact that we had a 2x on the inside. Again, that's the derivative of the 2x. Denominator for now is going to stay the same. Now, taking a look at this numerator, I believe that if we were to apply a Pythagorean identity once we have a tangent times a tangent, we could probably turn this into a secant cubed somehow. However, I'm going to say that seems like a lot of work, so what I'm going to do is clean it up to the best of my ability without using a Pythagorean identity, and we'll call it good after that. So in the numerator, I'm going to be distributing this 2 and secant of 2x and tangent of 2x to both of the terms inside this set of parentheses. We'll have 2 times the secant of 2x times the tangent of 2x times 1, and we'll distribute to the tangent of 2x as well, plus 2 times the secant of 2x times the tangent of squared of 2x, and then combine all of these factors together to get 2 times the secant cubed of 2x. All of this is going to be over 1 plus the tangent of 2x, quantity squared. Honestly, I'm content to leave it in that form for now. Just know that there are all sorts of trigonometric acrobatics that we could do with something as special as this.